Welcome to the Explainer. So let's get right to it. Is the crazy power of AI models like GPT just a fluke, something that happened because we made them bigger and bigger? Or is there a deep, fundamental reason they work so incredibly well? Today, we're diving into the theory that answers that very question.
You know, it's pretty amazing when you think about it. How can the exact same kind of AI understand a tiny little tweet and also digest and analyze an entire novel? That kind of flexibility is not an accident.
It's actually a core feature of the architecture that runs the whole show these days, the transformer. So whether we're talking about just a handful of words or literally hundreds of thousands, the transformer is built to take it all in. But how? And more importantly, is there a limit?
Right, so this leads us to one of the biggest questions in AI research. Is all of this power just about making things bigger, or is there some kind of secret sauce, a deeper principle that lets these models handle almost infinite context?
And that is the central mystery that a really groundbreaking new paper set out to solve. The researchers, Takashi Furuya, Maarten, and Gabriel Peyré, wanted to know once and for all if a transformer could theoretically learn from a context of any size. We're talking even an infinite one. This whole idea is what they call in-context learning.
No, what's so fascinating here is that this idea of a universal model, well, it's not new at all. To really get why this new paper is such a big deal, we actually have to take a quick look back.
Way back in 1989, researchers proved that even really simple neural networks were something called universal approximators. Fast forward to 2017, and the transformer is born with the famous "Attention is all you need" paper. People started poking at its universal nature pretty quickly, but it wasn't until this 2024 paper that we finally got a powerful and much more complete answer.
So, what on earth does universal approximator even mean? Well, to put it simply, it's the idea that a model's architecture is flexible enough to copy pretty much any continuous pattern or behavior, as long as you give it enough complexity to work with. It's kind of like having a block of marble so perfect that a master sculptor could carve absolutely any statue they could dream of. The architecture itself is that capable.
Okay, so how did the researchers prove this for something as complex as a transformer? The old math just wasn't going to cut it, especially when you're trying to deal with this mind-bending idea of an infinite context.
They used a really clever mathematical trick. See, the old way of thinking about context was just as a long list of separate words, but that becomes a nightmare to analyze when the list gets super, super long. So the new idea, and this is the key insight of the paper, was to stop thinking of it as a list and start seeing it as a probability distribution of tokens. It's a subtle shift, but it's brilliant because it lets them use powerful math to analyze any context size, small or infinite, all in the same way.
And this brings us to the formal name for what transformers do: in-context mapping. It's basically a function that takes an input and gives you an output. But here's the magic part. The function itself gets reshaped and redefined by the entire context you gave it. It's not a fixed function. It literally adapts on the fly.
I love this analogy. It's perfect. The transformer is like that master jazz musician. It doesn't just play a memorized song. It listens to the notes you give it, the context, and then improvises a brilliant solo, the output, that's perfectly in key with what it just heard. That's in-context learning. All right, let's get to the core findings of the paper. The researchers came up with two major theorems, one for each of the main flavors of transformer architecture. So on one side, you've got unmasked attention. Here, every part of the input can see every other part. This is really common in vision models. Then you have masked attention, where each part can only see what came before it. This is absolutely critical for language models like GPT, because you have to predict the next word without cheating and looking ahead. Now, for that unmasked case, their first theorem is just incredibly powerful. I mean, think about what this is saying. A single fixed-size transformer can learn any continuous task you throw at it. You don't need to make the model itself bigger or add more parts just because the context is more complex. It proves the architecture is just fundamentally, inherently capable, even with infinite inputs. And for the masked version, the one used for a language, their second theorem proves universal approximation there too. This is huge. Now, because language has this one-way flow of time, it needs a couple of extra mathematical rules. The context needs to be sort of well-behaved, but the paper shows that transformers naturally handle this. The main result is the same. They are universal learners. Okay, so we've got this fancy math proof. That's great for the researchers, but why should we care? Why does this theory actually matter for the future of AI? Well, first, and this is maybe the most important thing, it confirms that the magic of models like GPT isn't just some lucky accident. We didn't just stumble upon it by throwing more and more computers and data at the wall until something stuck. Second, it tells us that the transformer architecture itself is fundamentally sound. Its design is inherently, deeply capable of this universal learning. The blueprint isn't a hack. It's a solid, principled framework.
And what that all means is that researchers now have a rock-solid theoretical foundation to stand on. It gives everyone the confidence to build even bigger, better, and more reliable AI systems because they know the bedrock they're building on is mathematically proven.
But like any great piece of science, solving one big mystery just reveals a bunch of new ones. And the paper is very upfront about what it hasn't solved yet.
So what are those limits? What are the next big questions? The paper itself points to a few really interesting open areas.
This proof is what's called existential. It proves a transformer can learn anything, but it doesn't give you the exact recipe. For example, it doesn't say how deep the model needs to be to get a certain level of accuracy. It also shows some parts still need to scale up and that some assumptions for language models are pretty strong. But these aren't failures of the paper. No, they're the exciting new frontiers for the next wave of AI research.
So this proof really establishes a fundamental truth about one of the most important technologies of our lifetime. It tells us that, in theory, the learning potential of the transformer is limitless. It gives us a solid foundation for everything that's coming next, and it leaves us with one final, really tantalizing question to think about.